The sand plain shimmers beneath a noon sun, each grain reflecting light in restless patterns. Above, the water column seems almost empty, an expanse of blue without motion. But emptiness here is never to be trusted. Suspended in that blue is a predator honed into the shape of a blade, motionless, silver, a sliver of living metal that could be mistaken for a trick of the light. This is the barracuda, a hunter that thrives not by blending into reef crevices or burying into sand, but by erasing itself in open water, dissolving into glare until only its shadow betrays it. For prey, even that faint trace is often noticed too late. The secret of its vanishing act lies in its skin. Barracudas are clad in scales loaded with guanine crystals, microscopic plates that function as mirrors. Unlike pigments, which absorb or scatter wavelengths, these crystals reflect. The reflection is not random but organized, angled in layers that scatter light in all directions. When suspended in the column, the barracuda becomes a mirror of its surroundings, refracting the sand below, the blue above, and even the glimmers of sunlight dancing across the surface. Edges blur, outlines dissolve, and what remains is a distortion in water rather than a body. To the eyes of prey fish, especially those evolved to detect contrast and motion, the barracuda becomes a phantom. It is a predator that hides not in cover, but in optics. This camouflage is perfect for ambush because the barracuda is not a long-distance chaser. Unlike tuna or mackerel that power themselves across kilometers of open ocean, barracudas rely on sudden acceleration. Their bodies are built like javelins, long, slender, with reduced body wave compared to other predatory fish. When the strike begins, the head yaws first, locking target and aligning trajectory. The body remains rigid, minimizing turbulence that might warn prey. Then the tail delivers a single, explosive burst, a contraction so violent that it propels the barracuda several body lengths in less than a second. In this first step lies its power. Few fish in the reef can turn sharply enough to evade such speed. For prey, the moment of recognition and the moment of impact blur into one. The mechanics of this launch are as refined as any engineered system. The barracuda's musculature is packed with fast twitch fibers capable of delivering instant force. Its long vertebral column is designed for stiffness, allowing energy to channel directly into forward momentum rather than dissipating into side-to-side motion. Unlike sharks, whose sinuous swimming generates wake detectable by prey lateral lines, the barracuda's movement is economical and direct. In that single tailbeat, it creates more acceleration than many fish can muster in an entire sprint. The result is an attack that is over before the camera can pan, before the prey can pivot, before instinct translates into motion. Yet barracudas are not reckless sprinters, burning energy on chance. They are strategists, choosing ambush posts with care. Along the borders where reef meets sand, currents funnel baitfish in predictable streams. At channel mouths, tides drive small fish into narrow corridors, their paths compressed by geography. These are the hunting grounds of barracuda, places where prey is forced into linear movement, where sudden acceleration intersects certainty. Motionless above sand or hovering near coral heads, the predator becomes part of the landscape until a school drifts too close. Then silver steel ignites into motion, and panic tears through the column. Prey fish have evolved defenses of their own. Schools flicker, their bodies turning in tight synchrony to confuse a predator's strike. This collective motion is designed to overwhelm the attacker's targeting, replacing one fish with a blur of many. But barracudas are tuned to that very flicker. Their lateral line system, rows of sensory cells detecting water movement, is particularly sensitive to rapid amplitude changes, the jerks and wobbles that mark a wounded or startled fish. What is meant as confusion becomes invitation. A single fish that falters, that breaks rhythm, becomes a beacon to the predator. Lures used by fishermen mimic this very principle, wobbling in patterns that exploit the barracuda's bias toward irregular movement. In essence, flicker is both shield and betrayal, a defense that becomes a vulnerability under the gaze of this hunter. The strike is violent in its simplicity. The jaws, lined with sharp, dagger-like teeth, are not designed for chewing but for slicing. Barracudas shear prey into sections, swallowing chunks whole. Unlike sharks, which may grip and thrash, barracudas dispatch with precision. Their teeth interlock, forming scissors capable of cutting through bone and scale alike. For smaller prey, the suction of the sprint alone can carry them into the mouth. For larger prey, one bite cripples, a second ends. What follows is not wasteful tearing, but efficient consumption, energy converted quickly, risk minimized. Ecologically, barracudas occupy a liminal role between reef and open water. They patrol edges, connecting ecosystems that seem distinct, coral labyrinths on one side, sandy plains and pelagic blue on the other. Their presence shapes prey distribution, pushing schools into tighter formations, altering migration paths, and even influencing where juvenile fish settle. In some regions, barracudas act as keystone predators, thinning populations of mid-sized fish that would otherwise overwhelm reef resources. Their hunting does not simply remove individuals, it restructures communities. Yet these hunters are not without vulnerability. Juvenile barracudas themselves fall prey to larger predators, from sharks to groupers, and their mirror camouflage is less effective when their smaller size forces them into habitats closer to cover. Growth shifts them into open water ambush niches, and survival to adulthood depends on mastering both stillness and sprint. Even adults must navigate the costs of their strategy. Each burst of speed is metabolically expensive, relying on anaerobic muscle fibers that quickly fatigue. Failures deplete reserves. Thus, barracudas must weigh each strike, conserving energy until conditions align perfectly. Ambush is not about frequency, but precision. From a human perspective, barracudas carry an aura of menace, their long bodies and toothy grins immortalized in stories of sudden attacks. Yet most encounters with divers end in wary observation rather than aggression. Their curiosity reflects intelligence, an ability to recognize scale and threat beyond instinct. Still, the speed and ferocity of their strike remind us why they inspire both fascination and fear. To witness a barracuda's mirror sprint in clear water is to see physics made flesh, optics, mechanics, and biology, converging into a weapon so efficient it borders on elegance. In the end, the barracuda embodies a paradox. It hides by reflecting the world, then reveals itself in a burst that seems to break the rules of time. It thrives not on constant pursuit but on stillness, on patience distilled into sudden violence. In a sea filled with predators, its niche is defined not by size or strength alone, but by mastery of the first step, the acceleration that collapses distance into inevitability. For the prey, recognition comes too late, the flash of silver already upon them. For the barracuda, the ocean is not an endless void, but a stage where stillness becomes trap, reflection becomes cloak, and speed becomes the final truth. At first glance, the seafloor is still. Rocky outcrops rest like ancient ruins on the shelf, draped in fronds of kelp and scattered with sand that drifts lazily in the current. Nothing moves except the occasional flicker of a shrimp or the distant shadow of a cod weaving through the dim light. Yet hidden in this quiet tableau lies a predator whose presence is nearly impossible to perceive until the moment it strikes. The monkfish, often dismissed as grotesque or ugly, has mastered the art of invisibility, not through speed or elegance, but through a fusion of physics, patience, and deception. The body of a monkfish is less a streamlined hunter and more a flattened platform pressed against the substrate. Wide pectoral fins spread like wings, while the mottled skin mirrors the irregularities of stone, kelp, and sand. To bury itself, the monkfish does not simply wriggle downward, it engineers its cover. With fanning motions of its fins, it stirs sediment into suspension, creating a temporary cloud that resettles across its back. Grains flow into creases and ridges, coating the skin until the fish is indistinguishable from the terrain. Only the eyes protrude, swiveling independently, and one feature rises above the disguise, a filament extending from its head, tipped with a fleshy appendage. This is the Elysium and esker, the fishing rod and bait of one of nature's most inventive ambushers. The lure is not static. It wriggles with subtle precision, movements tuned to the expectations of local prey. In shallower waters, the esker may mimic the darting of a small minnow, flickering with just enough irregularity to catch the attention of passing fish. In deeper, darker habitats, it may glow with bioluminescent light, a beacon in the gloom where prey follow faint glimmers as potential meals. The deception is so convincing that fish approach willingly, even eagerly, mistaking the threat for opportunity. This inversion of roles, prey hunting the predator's bait, is the monkfish's genius. The seafloor inhales and the frame is suddenly empty. The strike itself is a marvel of rapid mechanics. Unlike predators that rely on muscular pursuit, the monkfish uses suction, turning water itself into a weapon. In a fraction of a second, the buccal cavity, its mouth and throat, expands violently. Skeletal slings of bone and ligament snap open, and the hyoid apparatus drops downward, creating an instant vacuum. Pressure inside the mouth plummets, and surrounding water rushes inward to equalize the difference. Prey caught in this sudden flow are dragged with it, funneled into the expanding jaws before any escape reflex can fire. It is not strength that captures them, but physics. The prey is carried by the medium it inhabits. For the unlucky fish or shrimp, there is no warning. One moment, the lure seems harmless. The next, the world itself collapses toward a dark cavern rimmed with sharp teeth. The speed of suction is astonishing. Buccal expansion takes only a few milliseconds, faster than the response time of most vertebrate nervous systems. By the time the prey's brain registers danger, it is already inside. Unlike the slicing bite of a barracuda or the constricting hold of a moray eel, the monkfish's strike is silent and total. The prey vanishes, water and all, into the waiting stomach. This strategy is perfectly matched to the monkfish's environment. On the continental shelves and slopes where it thrives, light is dim and temperatures are cool. Prey move more slowly in the cold, conserving energy in habitats where food can be patchy. For a predator, this means pursuit is wasteful. Energy budgets in such ecosystems favor stillness and precision, not chase. The monkfish invests in patience, waiting hours or even days in the same position, conserving energy until the lure succeeds. Each strike must count, but the efficiency of suction ensures that when prey approaches, success rates are high. This is why ambush specialists dominate in colder, darker habitats. They make the math work. The burial physics of monkfish hunting reinforce this economy. By fluidizing sand with fin movements, the monkfish removes itself from sensory fields. Many prey rely not on sight, but on lateral lines to detect vibrations in water or on electroreception to sense living bodies. A monkfish lying exposed might betray itself with faint ripples or electrical cues. But buried beneath sediment, only the lure moves. The body disappears into the background hum of the reef, while the esker remains as a lone anomaly. For prey, the calculation seems simple. Ignore the stillness, investigate the motion. Yet it is a trap that has been perfected over millions of years. The monkfish's adaptations extend beyond hunting to survival in its austere world. Its metabolism is tuned to long fasting periods, allowing it to endure when prey is scarce. Its body shape, flattened and wide, allows maximum stability against currents, minimizing energy spent on station holding. Even reproduction reflects the economy of its lifestyle. Females release enormous sheets of eggs, gelatinous veils that drift through the water column until they fragment and disperse. This strategy ensures wide distribution, hedging against the unpredictability of survival in deep, cold seas. From an ecological perspective, monkfish are more than curiosities of ambush. They help regulate populations of smaller fish and crustaceans, maintaining balance in communities that might otherwise tilt. Their presence ensures that no single species of prey dominates the shelf. In turn, monkfish themselves provide meals for larger predators, from sharks to seals, passing energy upward through the food web. Even their discarded eggs feed planktonic grazers, linking their reproduction to the smallest layers of the ecosystem. Despite their efficiency, monkfish remain vulnerable to human exploitation. Their camouflage does little against trawling nets, and their slow growth and reproductive strategies leave them sensitive to overfishing. In some regions, they are harvested as delicacies, their tails prized for firm flesh. Ironically, the very stillness that defines their predation makes them easy targets for human tools. Unlike barracudas or tuna, they do not bolt from disturbance. They wait, trusting camouflage even when nets descend. It is a reminder that strategies perfected for natural predators may fail against human industry. Yet in the realm of the natural, monkfish remain peerless examples of ambush design. Their strategy embodies the principle that the quietest killers win, not through pursuit, but through pressure. Where barracudas rely on reflection and speed, where moray eels lunge from crevices, where stingrays exploit suction from above, the monkfish makes the seafloor itself an accomplice. It transforms patience into weaponry, silence into inevitability, physics into capture. The image of a rock that grows a minnow and then inhales may seem surreal, but it is the essence of this predator's strategy. The monkfish is not beautiful in the way of reef fish or dramatic in the way of sharks, but its mastery lies in unseen perfection. The next time a shrimp pauses near what looks like a harmless lump of stone, the seafloor may exhale, and the frame will suddenly be empty. The mangroves breathe with the tide. Their roots, knotted like twisted fingers, rise from the mud and brace against the shallow current. Between them, channels open and close with the moon's pull, funneling the movement of water and life itself. In this stillness, where shade swallows sound, the water's surface looks empty, until it isn't. A faint ripple forms where nothing should move, a bow wave curling outward from an invisible mass just beneath. Then, in a sudden convulsion of muscle and jaws, the water detonates. A fish vanishes. Silence returns, broken only by the fading rings on the tide. The ambusher is a crocodile, a predator that has refined the art of patience into a strategy as old as the mangroves themselves. Crocodiles are survivors of an ancient lineage, their design perfected not by endless change, but by constancy. They do not need to chase across open water like tuna, nor rely on endurance like sharks. Instead, they turn the physics of rivers and tides into their weapons, placing themselves exactly where prey must pass and letting inevitability do the rest. The secret begins along their jaws. Running in neat rows are integumentary sensory organs, tiny black dots that appear like scattered freckles to the human eye. These organs are among the most sensitive mechanoreceptors in the animal kingdom, capable of detecting the slightest vibration in water. A struggling fish, a bird landing clumsily, even the faint ripple of an eddy forms a map that the crocodile can see without sight. In the dim mangrove shade, where vision fails, these sensors give the animal a perception as sharp as radar, translating disturbance into position, strength, and direction. The crocodile does not wait blindly. It is reading the water like a script. This sensory advantage is amplified by strategy. Crocodiles position themselves at choke points, creek mouths where the tide drains into channels, or narrow passes where fish are forced to swim in compressed lanes. Here, the current works as conveyor belt, delivering prey directly into range. Timing is everything. At slack tide, when water slows and visibility clears, fish funnel out of mangrove nurseries or estuarine pools, moving predictably into open sea. Crocodiles anticipate these patterns, aligning themselves so perfectly with the flow that they appear less like hunters and more like fixtures of the current. To the fish, the shaded silhouette is simply another route, another log, until the strike arrives. The mechanics of that strike are brutal efficiency. A crocodile's body may seem ponderous on land, weighed down by thick armor and short legs, but in water it transforms. The long tail, packed with muscle, stores elastic energy as it coils. In the instant of release, it uncoils like a whip, launching the animal forward with astonishing acceleration. The trunk provides leverage, channeling the burst into a straight, explosive lunge. Drag, which hinders most predators in shallow water, is minimized by the crocodile's low, streamlined profile. The head, narrow and flat, cuts through the current like a wedge, jaws opening only at the final moment to reduce resistance. The entire movement is over in less than a second. Jaws are the finale, but they are no less extraordinary than the burst itself. With one of the most powerful bites in the animal kingdom, crocodiles can deliver forces strong enough to crush turtle shells or bone. Their teeth, conical and interlocking, are not built for slicing but for gripping, ensuring that once prey is caught, it does not escape. Muscles that close the jaws are massive, but those that open them are weak, an imbalance that reflects their strategy. Seize first, hold relentlessly. Once the fish is in their grip, escape is impossible, dragged beneath the surface in a vortex of mud and bubbles. But crocodiles are more than stationary ambushers. Along coasts, they take voyages that would surprise many who see them only as river dwellers. They ride tidal eddies and warm plumes, drifting for kilometers along shorelines, conserving energy as currents do the work of transport. Salt glands hidden in their tongues allow them to process seawater without harm, balancing fluid and ion levels in a way most reptiles cannot. This adaptation opens new frontiers. Mangroves, estuaries, even open coasts become extensions of their hunting grounds. A crocodile may bask in a sunlit pool one day, then appear miles away at a coastal pass the next, carried by nothing more than tides and patience. Thermoregulation underpins these journeys. As cold-blooded reptiles, crocodiles cannot produce constant internal heat. Instead, they use daylight basking as thermal banking. Lying on sandbanks or mudflats, they soak in warmth until their bodies store enough energy to power hours of activity. At night, that stored heat fuels metabolism, digestion, and hunting. On overcast days, when basking is less effective, they often reduce movement, conserving energy until the sun returns. In this way, every decision, from strike timing to travel distance, is mediated by the balance of heat and tide. What makes crocodiles remarkable is not only their physiology, but their ecological insight. They do not waste energy chasing fish in open water. They wait at exits, predicting prey flow with uncanny accuracy. They do not patrol blindly along coasts, but exploit eddies, letting currents deliver them silently. They do not burn calories needlessly, but invest heat gained in sunlit hours into nocturnal strikes. These strategies reveal an animal not simply ruled by instinct, but fine-tuned by millions of years of natural selection to read and manipulate its environment. The impact of these predators extends beyond individual kills. By ambushing at creek mouths, crocodiles influence when and how fish leave mangrove nurseries, shaping migration patterns that ripple outward through the food web. Their predation on weak or unwary individuals strengthens schools by removing the vulnerable. And by moving between rivers and coasts, they link ecosystems, transferring nutrients and shaping community structure across boundaries. A crocodile is not merely a local predator, but an ecological bridge, threading together mangrove shade, tidal currents, and coastal seas. To the human eye, the ambush may seem simple: stillness, strike, silence. But beneath it lies complexity layered across senses, physics, and ecology. A crocodile waiting in mangrove shade is not idle, it is calculating. It knows where the tide will funnel fish, how the current will conceal its ripple, when the slack will open opportunity. It reads disturbances invisible to others, translating ripples into prey maps. It harnesses stored elastic energy in muscle, turns the drag of shallow water into leverage, and transforms heat from the day into power for the night. As the tide shifts once more and the mangrove roots stir in the ebb, the crocodile sinks back into stillness. To the untrained eye, it vanishes, a log among logs. But somewhere in that shadowed stillness, integumentary sensors hum with the passage of fish, muscles coil with stored potential, and ancient patience measures time not in minutes, but in cycles of tide and sun. In this world, victory belongs not to the fastest swimmer nor the strongest bite alone, but to the predator that has learned the rhythm of water itself. Learn the tide, and you own the choke point. The open sea is deceptive in its vastness. To a small fish, it seems like a refuge of endless water, a place where safety lies in scattering into 3 dimensions. Yet in the deep blue, even vastness can be turned into a trap. Off the coast of Alaska, in the cold green water of summer feeding grounds, the surface boils, not from storm, but from whales at work. A column of bubbles spirals upward from the depths, black and solid as a rising wall. Small herring and capelin, startled and confused, dart inward rather than out, compressed by currents they cannot escape. Within seconds, a school that had filled a stretch of ocean is compacted into a single target. Then the water parts as a massive mouth breaches the surface, pleats unfurling, throat expanding, and hundreds of fish vanish in one effortless gulp. This is bubble net feeding, one of the most sophisticated hunting strategies in the marine world, practiced by humpback whales in a handful of regions. It is not the work of a lone predator, but a coordinated performance, each role as essential as the next. One whale begins as the caller, emitting low-frequency feeding cries that reverberate through the water, driving prey into tighter schools. Others act as herders, circling beneath the fish to direct movement upward. And at the heart of the strategy are the net layers, whales that spiral upward while expelling steady streams of bubbles from their blowholes, weaving a cylinder of air into the water column. To the fish, these bubbles are not harmless. They alter light, density, and pressure, creating both visual and physical barriers. To the whales, they form a corral, a wall that moves as they command. The physics of this trap are remarkable. When bubbles rise, they displace water, lowering density and creating localized upwelling flows. Small fish, which rely on fine-tuned control of their swim bladders for buoyancy, struggle in such turbulent water. The upwelling disorients them, pushing them toward the center line where the water is more stable. At the same time, the reflective surfaces of bubbles appear as barriers, tricking the fish into perceiving a wall. Hemmed on all sides by turbulence and optics, they compact into a dense ball, a single swarm where seconds before they had been scattered. In nature, prey depend on spreading out to dilute risk. The bubble net flips that rule, forcing prey into concentration until the strike becomes irresistible. Timing is critical. As the school compresses, the whales align below, coordinating by sound. When the moment comes, they surge upward together. A single whale can engulf thousands of liters of water in one lunge, pleated throat grooves expanding like an accordion to triple or quadruple the volume of the mouth. The angle of gape is precise, minimizing drag while maximizing intake. Many roll their bodies as they ascend, using gravity to pour fish toward the gullet. By surfacing in unison, mouths agape, they create a collective strike that resembles a floating fortress breaching from below, an eruption of baleen and water. For the fish trapped inside, the event is not a chase but a collapse of space itself, survival reduced to the impossible task of outswimming a wall of baleen plates. The efficiency of bubble net feeding cannot be overstated. For an animal as massive as a humpback whale, energy budgets matter. Each lunge, though powerful, consumes significant calories. To feed effectively, they must maximize return on each strike. By concentrating prey into dense schools, bubble nets ensure that a single mouthful delivers hundreds of calories in one effort. In cold waters where metabolism runs high, this strategy is the difference between thriving and starvation. It is no coincidence that humpbacks employ bubble netting in regions where fish are abundant but mobile, fjords, headlands, and krill fronts where currents compress prey against natural boundaries. The whales add the missing element, turning geography and physics into an engineered trap. The cultural element of bubble net feeding is as fascinating as its mechanics. Not all humpbacks know this strategy. It is learned behavior, passed from whale to whale, and practiced in specific populations, such as those in the North Pacific. Some individuals specialize in certain roles. A particular whale may become known as a caller, its feeding cries distinct and recognized by its companions. Others excel at net laying, their spirals precise and consistent. This division of labor suggests not only intelligence but social memory, a cooperative culture that extends across generations. In the fluid world of the ocean, where no nets or tools are fixed, whales build their traps from sound and breath, ephemeral yet repeatable, a shared invention woven into tradition. For prey species, bubble netting has shaped behavior as well. Fish herded by whales learn to flee bubble columns, but the sheer unpredictability of the attack makes resistance futile. Unlike sharks or seals, which approach visibly, whales turn the very medium of life into weaponry. The fish cannot adapt quickly enough because the strategy does not rely on physical pursuit. It manipulates physics itself. In regions where bubble netting occurs, Schools become denser, more reactive, and more tightly synchronized, yet these adaptations only enhance the whale's success. A tighter school means a tighter ball when trapped. Irony folds survival into vulnerability. Beyond the act of feeding, bubble nets carry broader ecological implications. By concentrating fish and krill, whales inadvertently provide opportunities for other species. Seabirds dive into the chaos, snatching prey flushed upward by the rising column. Sea lions and smaller fish exploit the disorientation, picking off stragglers outside the main strike. In this sense, the whales act as ecosystem engineers, creating temporary explosions of activity that ripple across trophic levels. Each feeding event is both consumption and creation, destroying one pattern of life to birth another in its wake. From a scientific perspective, bubble netting challenges our assumptions about non-human engineering. The net is not tangible, not constructed from material, yet it operates with all the hallmarks of technology: design, purpose, efficiency, and cooperation. It is a tool made of air and sound, wielded collectively by giants that breathe through lungs like ours, yet reshape the sea with breath alone. It reminds us that invention is not limited to hands or tools. Evolution can write intelligence into any form that survives, and here it has written architecture into whales. As the hunt concludes, the whales drift at the surface, water cascading from their baleen as they filter fish from sea. Their great bodies glisten black against the backdrop of fjords, breath erupting in plumes that mingle with gulls diving overhead. Then, with quiet dignity, they sink again, vanishing beneath the surface to reset the trap. The ocean stills, schools scatter, and for a moment the illusion of freedom returns. But somewhere below, bubbles are already rising, coiling into the shape of another net, another wall, another collapse of space. In the end, bubble net feeding is more than spectacle. It is testimony to the capacity of life to engineer with what is at hand. Air, sound, and flow, ephemeral and invisible, become reusable architecture, a net that vanishes as quickly as it forms, but works with relentless success. For the herring above the fjord, the ocean may seem infinite, yet the whales prove otherwise. Vastness can be folded into a cylinder, freedom can be compressed into a mouthful, and in that fleeting wall of bubbles, the architecture of survival is rewritten. On a sunlit reef flat, where the sand stretches pale and unbroken between coral towers, a small shadow drifts lazily near the bottom. It seems harmless, even vulnerable, just another tiny fish with round eyes and stubby fins, slow-moving compared to the darting wrasses and glinting anchovies that streak past in schools. A grouper spots it and surges forward, jaws opening in a rush of water. But in an instant, the shadow doubles, then triples in size. Spines snap outward, the body inflates like a balloon, and the grouper breaks in shock. The predator, once intent on swallowing, veers aside in confusion. What moments earlier looked like an easy meal now appears unmanageable, too large to fit in its gape, and too bristling with danger to risk testing. The tiny fish drifts on, victory secured not by speed or strength but by transformation. This is the puffer fish, an improbable survivor that rewrites the rules of defense. The inflation that defines puffers is more than a parlor trick. It is a finely tuned system of mechanics and physiology that exploits the limitations of gape-limited predators. When threatened, a puffer gulps water, sometimes air if cornered at the surface, into a specialized, highly elastic stomach. Muscles lock the esophagus and pylorus, preventing the water from escaping backward or forward. The result is rapid expansion, the body doubling or tripling in volume in seconds. Beneath the skin, collagen fibers stretch, while skeletal elements shift to accommodate the ballooned form. At the same time, dermal spines, normally lying flat, erect outward, adding a sharp armor to the inflated globe. To a predator, the shift is overwhelming. A small, soft-bodied fish instantly becomes a spiny, ungraspable ball, resistant to jaws and claws alike. This inflation comes at a cost. The act is metabolically taxing, requiring rapid muscular contractions and straining tissues. Once inflated, the fish is clumsy, unable to swim efficiently until it deflates. But the trade-off favors survival. Predators learn quickly that puffers are not worth the trouble. One failed attempt imprints a lesson across the reef. Leave these fish alone. And behind this mechanical defense lies another, more insidious layer, the chemistry of toxin. Pufferfish carry tetrodotoxin, one of the most potent natural poisons known. Unlike venoms injected through fangs or stingers, this toxin is born within the tissues, concentrated especially in the liver, skin, and ovaries. Its origin lies not in the fish themselves, but in symbiotic bacteria, species of Vibrio, Pseudomonas, and others that live within their bodies. The fish become vessels for bacterial biochemistry, harnessing toxins that block sodium channels in nerves and muscles. The effect is paralysis, and in sufficient doses, death. For predators, even sampling a puffer can mean disaster. On coral reefs, the presence of tetrodotoxin spreads through the community as learned avoidance. Predators that survive an encounter, whether by spitting out an inflated puffer or tasting a small dose of toxin, remember. Their reactions are noticed by others, and over time, puffers acquire a near universal aura of warning. Unlike bright colors or rattling tails, their defense is quiet, chemical, and profoundly effective. They are reminders that survival does not always come from speed or stealth. Sometimes it comes from being the meal no one dares to eat. But puffers are not defined only by defense. In shallow, sandy plains of the Pacific, males become artists, transforming emptiness into architecture. With patient sweeps of their fins, they carve circular ridges into the sand, radiating outward in intricate symmetry. Each ridge channels water flow, funneling fine sediments into the center. The result is a mandala nearly 2 meters across, patterned with peaks and valleys that ripple with light. Within the central depression, the male deposits shells and fragments, decorations chosen with deliberate care. This construction is not shelter nor trap, it is courtship. For females cruising above the reef, the circles are signals of fitness. Symmetry demonstrates the male's persistence and control. The ability to manipulate hydrodynamics reveals strength and endurance. In a world where predators and currents erase imperfections quickly, only the most skilled builders maintain flawless designs. When a female chooses a circle, spawning occurs at its center, and the eggs are protected by the fine sediments accumulated there. For the male, the act of architecture is both investment and advertisement, proof of his ability to survive despite the costs of drawing attention in a world of ambush predators. For the female, the circle is assurance that her offspring will inherit both skill and resilience. These sand circles are more than spectacle, they are physics applied with instinct. Hydrodynamic ridges alter water flow, concentrating light sediments where eggs can be cushioned and anchored. Larger shells placed in the center act as stabilizers, reducing turbulence that might scatter the eggs. It is engineering without blueprint, design honed by trial and error across generations. In human eyes, the mandalas resemble art. In ecological terms, they are architecture tuned to survival. The dual nature of puffers, their defensive chemistry and their constructive courtship, underscores the complexity of survival strategies in the ocean. They are not apex predators, not fleet swimmers, not armored giants. Instead, they thrive by making themselves costly to eat and valuable to choose. Their role in ecosystems reflects this balance. By resisting predation, they persist in high numbers, feeding on algae, invertebrates, and detritus, helping regulate growth on reefs. By building circles, they disturb sediments, oxygenating the seafloor and altering microhabitats for worms and crustaceans. Their survival strategies ripple outward, shaping ecosystems in subtle but enduring ways. Humans too have entered the puffer's story. In parts of Japan, pufferfish, known as fugu, are prized as delicacies. Prepared correctly, the flesh is safe and tender, but the risk lies in error. Improper handling of the toxin-laden organs can render a meal lethal. Strict preparation rules and licensing systems govern its consumption, ensuring that only the most skilled chefs serve it. The allure lies not only in flavor but in danger, the knowledge that a single mistake could be fatal. It is a reminder of how closely our species dances with risk in pursuit of taste, and how a small fish, armed with bacterial chemistry, commands reverence even on human plates. To stand on a reef and watch a puffer inflate is to witness the improbable made real. A tiny fish doubles in size before your eyes, a balloon bristling with spines, then deflates as if nothing had happened. To dive over a sand flat and find a perfect circle etched into the bottom is to see geometry carved by fins, architecture born of instinct. In both cases, the puffer rewrites assumptions. The weak are not always vulnerable, the small are not always powerless, and even the most unassuming creatures may hold both the deadliest toxins and the most delicate artistry. In the end, the pufferfish survives by embodying paradox. It is both prey and untouchable, both humble and extraordinary. Its defenses lie not in pursuit but in refusal, not in invisibility but in deterrence. Its legacy lies not only in chemistry but in circles drawn on sand, patterns that vanish with the tide, but leave echoes in memory. On coral reefs where everything hunts and everything is hunted, the pufferfish proves that survival can be engineered from bacteria, inflated from water, and drawn into perfect symmetry beneath the sun. Defense chemistry and hydrodynamic design, two improbable strategies, united in one fish that should not succeed, yet does. On the shallow reef, where shafts of sunlight ripple across the sand and currents carry clouds of plankton between corals, a tiny burst of orange flashes like a signal flag. The fish seems impossibly bold, weaving between fleshy tentacles that sway like a living minefield. A passing wrasse darts too close, then breaks suddenly, veering away as though the water itself had become electrified. The clownfish slips deeper into the anemone's embrace, its bright stripes vanishing among tentacles that could paralyze or kill almost anything else that dares to enter. For this fish, however, the lethal curtain is sanctuary. Here, death itself has been rewritten into fortress walls. The key to this improbable alliance lies in chemistry. Sea anemones are cnidarians, armed with nematocysts, microscopic harpoons that fire in response to touch, injecting venom capable of stunning fish many times larger than a clownfish. Yet the clownfish swims freely through these tentacles, unscathed. This immunity is not innate but carefully negotiated. When a young clownfish first encounters an anemone, it does not plunge in recklessly. Instead, it performs a stepwise acclimation, brushing gently against tentacles and retreating, coating its skin with mucus from the anemone itself. Over time, its own mucus develops a cocktail of compounds that mimic the host's chemical profile, preventing nematocyst discharge. In effect, the fish cloaks itself in biochemical disguise, convincing the anemone that it belongs. What would be a death sentence for most reef dwellers becomes a welcome mat for one. From this chemical truce emerges a partnership of profound mutual benefit. The clownfish gains protection few other small reef fish can match. Predators that might snap up a bright orange target are halted at the electric fence of stinging tentacles, but the anemone gains just as much. Clownfish are vigilant sentinels, darting out to chase away butterfly fish or other intruders that would nibble at anemone tissue. They fan water constantly with their fins, increasing circulation around the tentacles and delivering fresh oxygen. Their waste, rich in nitrogen, fertilizes symbiotic algae living within the anemone's tissues, boosting photosynthesis and growth. The ledger of benefits runs both ways, a microeconomy where defense, fertilization, and cleaning are exchanged for sanctuary. In ecological terms, it is one of the most iconic examples of mutualism on the reef. The partnership does not end with survival, it extends into architecture. Clownfish are meticulous caretakers of their territory. They remove debris and fan sand from the anemone's base, keeping the substrate clear and preventing smothering. They chase away small invertebrates that might settle and compete for space. When breeding, they lay eggs near the base of the anemone, often on a cleared patch of rock kept scrupulously clean by constant attention. Males guard and fan the clutch, ensuring oxygenation and deterring predators. In this way, the anemone becomes not only fortress, but nursery, a lethal tentacle canopy transformed into cradle by the presence of its tiny tenant. The social life of clownfish adds another layer of intrigue. Within each anemone lives a structured hierarchy, ruled by a dominant female. Below her is the breeding male, and beneath him, a ladder of subordinate non-breeders, each ranked by size. This hierarchy is dynamic but strict. Should the female die, The breeding male undergoes sex change, transforming into the new dominant female. The largest subordinate then matures into the breeding male. This system, known as protandry, ensures that every territory maintains a breeding pair, stabilizing population structure despite constant threats from predators and environmental change. It also prevents chaos within the group. Competition is regulated not by constant fighting, but by growth suppression, with smaller fish deferring until opportunity arises. This ladder of dominance interacts directly with the anemone's biology. The size of the host anemone often limits the number of fish it can support. Larger anemones can house multiple subordinates, creating miniature societies beneath their tentacles. Each individual contributes indirectly to the host's health, fanning water, defending against small predators, and recycling nutrients. Thus, the anemone is not only fortress and nursery, but also stage for complex social drama, where life histories unfold according to both biology and circumstance. The ecological role of clownfish-anemone partnerships ripples outward across the reef. By defending their hosts, clownfish reduce predation pressure on anemones, allowing these sea cnidarians to thrive in competitive reef environments. Healthy anemones, in turn, provide shelter not only for clownfish, but also for small invertebrates and commensal species that hide among tentacles. Clownfish waste fertilizes not just the host, but nearby algae and seagrass, subtly influencing nutrient cycles. These partnerships may occupy only small patches of reef, yet their impact extends beyond their immediate footprint, shaping patterns of survival and competition in surrounding communities. Human fascination with this partnership has only grown. The striking colors of clownfish, coupled with their iconic association with anemones, have made them staples of aquaria worldwide. Yet in captivity, the balance is delicate. Anemones require precise conditions, and without the fish to fan and clean them, they often decline. Likewise, clownfish without anemones lose their fortress, their behavior altered in subtle ways. The interdependence that defines them in the wild proves difficult to separate. Their popularity has sparked conservation questions. The very bond that ensures their survival on reefs makes them vulnerable to collection. Sustainable management of both fish and anemones is essential if this partnership is to endure beyond glass tanks. For all their fame, clownfish are not universal across oceans. They inhabit specific regions, primarily the Indo-Pacific, and are absent from the Atlantic. Their anemone partners, too, are limited in distribution. This means the fortress strategy is both powerful and fragile, tied to the presence of suitable hosts. Without anemones, clownfish cannot survive long. Without clownfish, anemones suffer more predation and stress. Their destinies are entwined, each incomplete without the other. To watch a clownfish vanish into anemone tentacles is to see survival inverted. The very structures designed to kill become guardians. A predator approaching the anemone halts not from the fish's bravery, but from the stings that await. Yet within, the fish thrive, breeding, cleaning, and socializing under the cover of nematocysts. It is as though the moat of a castle were filled not with water but with poison, and within its walls, the inhabitants carried on untroubled, safe from armies outside. The story of clownfish and anemones is, at its core, about transformation, of danger into refuge, of predation into partnership. The anemone's tentacles remain lethal to nearly everything else on the reef, yet they shelter and sustain one of its most iconic fish. The clownfish, in turn, amplifies the anemone's survival, ensuring its place among corals and currents. Together, they turn competition into cooperation, a fortress into a nursery. On the reef, where survival is often measured in speed, stealth, or size, the clownfish and anemone prove that life can also endure through alliance. Chemistry becomes trust, territory becomes cradle, and hierarchy ensures continuity. In a world where most partnerships are fleeting or one-sided, theirs stands as fortress and family both. In the living architecture of tentacles and stripes, the reef reminds us that even the deadliest weapons can, under the right circumstances, be transformed into sanctuary. On a clear morning in the Indo-Pacific, the reef awakens in a blaze of color. Schools of antheas shimmer like orange embers above corals, parrotfish scrape at algae, and a lone grouper hovers in the shadows of an overhang. Among this bustle, a silhouette moves with unhurried purpose. Broad-bodied, thick-lipped, and crowned with a prominent hump on its forehead, the Napoleon fish, also called the humphead wrasser, glides into view. It is a giant among reef fish, often reaching over 2 meters in length and weighing more than 100 kilograms. Yet it moves with the slow grace of an animal that has little to fear. For this giant, power is not about speed or stealth, it is about jaws that can solve problems no other fish dares to attempt. The feeding technique of the Napoleon fish is nothing short of extraordinary. When faced with a clam too large to swallow or a snail encased in stubborn armor, it does not abandon the meal. Instead, it employs brute force and precision combined. With a sudden twist of its body, it seizes the shell in its jaws and slams it against a hard substrate, a rock, coral head, or even the reef itself, until the shell fractures. Few other fish have both the strength and the behavioral ingenuity to use the reef as an anvil. Inside the cavernous mouth, hidden behind those thick lips, lie pharyngeal teeth, crushing plates embedded in the throat. Once the shell is weakened, the wrasser maneuvers it back into these grinding jaws, pulverizing the fragments into digestible pieces. What other reef residents regard as impenetrable, the Napoleon fish converts into nourishment. This ability gives the wrasse access to prey unavailable to most. Hard-shelled mollusks, sea urchins, crustaceans, and even starfish become staples of its diet. Most remarkable of all is its predation on the crown-of-thorns starfish, a creature notorious for its destructive potential. Covered in venomous spines and armed with a stomach that extrudes to digest live coral tissue, the crown-of-thorns can devastate reefs during outbreaks, stripping vast areas of coral within weeks. Few predators dare to challenge it. Yet the Napoleon fish bites directly through its armored surface, immune to its venom. By consuming these starfish, it plays an outsized role in preserving the balance of reef ecosystems. The importance of this role becomes clear when outbreaks occur. Crown-of-thorns populations periodically explode, driven by nutrient runoff, overfishing of their competitors, or shifts in ocean conditions. When unchecked, they can overwhelm corals, reducing vibrant reefscapes to skeletal rubble. But in regions where large wrasses still thrive, outbreaks are dampened. By removing adult starfish and reducing reproductive pressure, Napoleon fish act as biological control agents, defenders of the very structures that shelter countless reef species. In a world where coral reefs face mounting threats from climate change and pollution, the presence of a fish capable of eating coral's most dangerous enemy is more than coincidence. It is ecological necessity. Yet for all their power, Napoleon fish are not apex predators in the conventional sense. They do not chase down schools of fish or dominate with aggression. Their strength lies in versatility, patience, and problem-solving. They investigate crevices, roll rocks, and pry prey from hiding places. They are slow but deliberate, each movement suggesting calculation. On healthy reefs, their presence is unmistakable, a solitary giant roaming among smaller fish, capable of feats no others can replicate. Their biology, however, carries one of the most fascinating twists in the animal kingdom: protogynous sex change. Napoleon fish are born female. In their early years, they live as smaller orange to pink individuals, blending among the reef's mid-sized fish. As they mature, some remain female, contributing eggs to the population. But when a dominant male is absent or when social conditions require, the largest females transform into males. Their coloration deepens into iridescent blues and greens, their foreheads grow the characteristic hump, and their reproductive organs restructure entirely. This transformation ensures that breeding groups always maintain males, stabilizing population dynamics. This life history, however, carries consequences for conservation. Because only the largest individuals become males, protecting them is critical for reproduction. Overfishing disproportionately removes these giants, skewing sex ratios and collapsing breeding potential. In some regions, demand for live reef fish in luxury markets has driven sharp declines in their numbers. Without large males, spawning aggregations fragment and recruitment falters. The very trait that stabilizes populations under natural conditions becomes a vulnerability under human exploitation. Understanding the importance of Napoleon fish means recognizing their place as keystone species. They are more than one predator among many. They are guardians of reef structure and function. By eating crown-of-thorns starfish, they preserve corals. By cracking hard-shelled prey, they influence the distribution of mollusks and crustaceans. By patrolling reefs as giants, they alter the behavior of smaller fish, subtly shaping community dynamics. Their loss would ripple outward in ways that far exceed their numbers. And yet, despite their size and strength, they carry a gentle aura. Divers often describe encounters with Napoleon fish as inquisitive rather than intimidating. They approach slowly, lips protruding, eyes scanning with curiosity. Some even linger, following divers through coral channels as though observing rather than avoiding. This gentle presence belies the force hidden in their jaws, the ecological weight of their role. In many ways, they are paradox embodied. Gentle giants with crushing power, reef saviors threatened by human demand. Their survival is tied to our awareness. In marine protected areas, where fishing pressure is reduced, Napoleon fish still thrive, growing to their full sizes and fulfilling their ecological roles. On unprotected reefs, their absence is felt not only in missing giants but in weakened coral defenses. To lose them is to lose more than a fish. It is to weaken the very architecture of reefs. To witness a Napoleon fish in action is to see adaptation at its most inventive. A clam, locked in armor, is no puzzle. A starfish, bristling with venom, is no threat. The wrasser turns obstacles into opportunity, predators into prey, shells into meals. Its biology is a reminder that survival does not always favor speed or stealth, but ingenuity and persistence. In the grand mosaic of reef life, it is a piece that holds the pattern together. And so, beneath the turquoise shallows of the Indo-Pacific, the Napoleon fish continues its slow patrols. It is at once engineer, guardian, and survivor. A massive wrasser slams a clam against rock, the fragments scattering like broken glass. Later, it chews methodically through a crown-of-thorns star, venom neutralized by the strength of its jaws. Around it, the reef endures, vibrant and alive, safeguarded in part by the bite of a single fish. A gentle giant, a problem solver, and a savior of corals, the Napoleon fish proves that sometimes survival comes not from dominating the reef, but from knowing how to crack its toughest secrets. Night settles over the reef wall like a curtain of ink. Daytime fish vanish into crevices, parrotfish encase themselves in mucus cocoons, and the water column empties of its bright daytime schools. In this hush, shadows lengthen, and out of the crevices a new cast of hunters emerges. Among them is one of the reef's most enigmatic predators, the moray eel. Its head protrudes from a dark hole, jaws rhythmically gaping in a motion often mistaken for aggression, but in truth, essential breathing. The body remains hidden, winding deep into the rock, coiled in labyrinthine passages of limestone and coral. When the strike comes, it is not with the streamlined grace of a barracuda or the open-mouthed sweep of a grouper. Instead, it is an eruption from stillness, an ambush perfected for tight quarters. And when the prey struggles, the moray unveils its secret weapon, a second set of jaws, sliding forward from its throat to seize the victim and drag it deeper inside. This adaptation, known as the pharyngeal jaw, is almost alien in its function. Most fish possess pharyngeal jaws of some kind, small toothy structures in the throat that grind food. But morays have taken this anatomy to an evolutionary extreme. Their pharyngeal jaws are highly mobile, mounted on muscular slings that allow them to project forward into the oral cavity. When a moray clamps its outer jaws on prey, the pharyngeal jaws shoot forward, seize the struggling fish, and haul it backward into the gullet. It is a feeding system reminiscent of science fiction, an echo of cinematic monsters, yet entirely real and unique among reef predators. This dual jaw system compensates for the moray's limitations. Unlike many predatory fish, they lack the ability to create powerful suction with their mouths. Their narrow skulls and reduced opercular cavities make suction feeding inefficient. Instead, evolution gifted them with reach. When backing space is limited, when suction is impossible, the pharyngeal jaws extend the predator's grip, transforming the throat itself into a weapon. The strike unfolds in seconds. A small damselfish hovers too close to a crevice. From the darkness, the moray's head explodes outward, teeth glinting under the moonlight that filters from the surface. The outer jaws seize first, curved teeth designed not for cutting, but for holding, their backward-pointing shape preventing escape. Then, almost imperceptibly, the throat convulses. Muscles contract, and the pharyngeal jaws surge forward, clamping onto the prey like a second mouth. The fish is pulled inside, vanishing into the labyrinth of the moray's body. Unlike predators that swallow prey whole with suction, morays drag their meals inward, one grip at a time, until nothing remains outside. The environment they inhabit makes this system indispensable. Morays favor crevices with geometry that amplifies ambush potential. L-shaped bends, T-intersections, and narrow fissures provide optimal positions, allowing them to coil their long bodies deep inside while keeping only the head exposed. From these vantage points they strike outward, then retreat immediately into shelter. Backing into such tight spaces would be impossible for most predators. Without suction feeding, they would lose prey. But for morays, the pharyngeal jaws ensure that once contact is made, capture is inevitable. Reach, not retreat, defines their hunting. Senses too reflect their nocturnal niche. Morays rely heavily on smell rather than sight, their nostrils marked by elaborate tubular structures that increase sensitivity. Even in darkness or turbid water, they patrol with confidence, following chemical cues left by stressed or injured fish. This reliance on olfaction explains their tendency to linger with mouths agape, pumping water over olfactory chambers as well as gills. In the nighttime reef, where vision fades and currents shift constantly, smell becomes the most reliable map. To prey hiding among corals, the eel may appear oblivious, but it is tracing their presence with invisible precision. The moray's ecological role is shaped by this unique hunting style. They specialize in prey that shelters among reefs, fish that wedge into crevices, crustaceans scuttling beneath ledges, octopuses shifting between holes. Their long, flexible bodies allow them to invade hiding places inaccessible to bulkier hunters. In this way, they exploit a niche few others can. Their strategy influences the behavior of prey communities, teaching small fish to avoid the entrances of crevices after dusk, altering where shrimps forage, even shaping the nocturnal rhythms of the reef. Yet morays are not always solitary hunters. In a fascinating twist, they sometimes form partnerships with groupers, engaging in cooperative hunts documented across multiple reef systems. The grouper, a daytime predator that struggles to extract prey from crevices, signals to a nearby moray with a rapid body shake or headstand. If the moray responds, the pair patrol together. The grouper flushes prey into open water, where its speed and gape give it advantage. The moray dives into crevices, driving prey outward or seizing it in its own jaws. Together, they access more habitat than either could alone. These collaborations, fleeting yet effective, reveal a level of interspecies coordination rare in fish. It is not altruism but mutual benefit, two predators doubling their reach. The appearance of a moray eel contributes to its eerie reputation. Their scaleless skin gleams with muted greens, yellows, or browns, sometimes patterned in intricate mosaics that blend with reef rock. Their jaws, perpetually gaping, expose curved teeth that look menacing even when the animal is simply breathing. For divers, encountering a moray in its crevice can feel unsettling, as if being watched by a lurking serpent. Yet most attacks on humans occur only when provoked, when hands stray too close to a defended lair. In truth, morays are shy, relying on their shelters for security as much as for hunting. The physiology of these animals underscores their role as specialists. Their bodies are elongated, lacking the pectoral and pelvic fins that would hinder entry into tight holes. Their dorsal fins run along the length of the body, giving them ribbon-like flexibility. Musculature is distributed for bursts of power rather than sustained speed. They are ambushers, not sprinters, a design perfected for striking from concealment rather than pursuing across open water. Even their dentition is specialized. Some species have narrow, needle-like teeth suited for gripping fish, while others bear molar-like plates capable of crushing crustaceans. Each adaptation reflects an evolutionary response to the challenges of reef crevices. In ecological terms, morays are regulators of reef balance. By preying on mid-sized reef fish, they prevent certain species from monopolizing shelter. By consuming crustaceans, they influence populations of grazers and cleaners. By venturing into cracks, they reduce the number of safe havens for prey, forcing adaptations in behavior and community structure. Their role is not as obvious as sharks or barracudas, but it is no less essential. The reef's architecture, with its endless holes and corridors, would host very different communities without the presence of these serpentine hunters. As night progresses, the moray eel continues its patrol, slipping from one crevice to another, vanishing into shadows only to emerge elsewhere. Each strike is sudden, decisive, aided by jaws within jaws that make escape impossible once contact is made. To watch one hunt is to glimpse evolution's ingenuity, a predator that overcame the limitations of suction and speed with an anatomical innovation so startling it seems unreal. In the maze of the reef, where shelter and shadow define the battlefield, speed alone is not enough. Success belongs to those who can reach where others cannot, who can draw prey deeper rather than chase them outward. The moray eel, with its twin jaws and serpentine body, embodies this truth. It is a reminder that survival in the ocean is not only about power or grace, but about invention. In the silence of night, when a bow wave forms where nothing should move, and a second set of jaws surges from the throat, the reef reveals one of its strangest, most ingenious hunters. In this labyrinth, reach beats speed. At dawn, the mangrove shallows glow with shifting light. Sunbeams slip between the roots, drawing luminous stripes across the water. Small fish hover in the calm backwaters, darting between shadow and glimmer. The scene is peaceful, almost delicate, until a shape glides through. A nearly invisible bell, its trailing filaments drifting like threads of glass. The fish barely notice, brushing too close, and in the next heartbeat one goes rigid. Muscles seize, fins quiver, and it begins to sink. The predator is no muscular hunter, no toothy ambusher, but a box jellyfish, a creature that kills with physics and chemistry at a scale too small for the naked eye to see. Box jellyfish are masters of invisibility. Their bells are nearly transparent, refracting little light, allowing them to drift unnoticed among mangrove shadows or across sunlit lagoons. Yet they are far from mindless drifters. Along the edges of their cube-shaped bells sit clusters of sensory organs called rhopalia, and within these structures lie something almost unthinkable for a jellyfish: true eyes with lenses, corneas, and retinas. Some of these eyes point upward, detecting the contrast of mangrove canopy against the sky. Others face sideways, gauging light patterns and obstacles. Together they provide a primitive but astonishing vision system, allowing box jellies to actively steer rather than passively drift. They can track edges, avoid routes, and position themselves along shadow lines where prey is likely to travel. In a lineage defined by simplicity, box jellies have invested in sight. But it is not vision that makes them deadly, it is the weaponry strung invisibly behind them. Each trailing tentacle carries thousands of nematocysts, microscopic capsules loaded with coiled tubules tipped by venomous harpoons. The physics of their deployment is one of nature's most extreme feats of acceleration. Inside the capsule, osmotic pressure builds, charged by ions pumping across membranes. When triggered, the capsule fires in nanoseconds, the tubule uncoiling and shooting outward with explosive force. The tip penetrates skin or scales, delivering venom directly into tissue. To prey, the strike is instantaneous, bypassing muscle reflexes, overwhelming with speed. It is not a contest of chase or endurance, but of physics. The faster weapon wins. Spacing of these nematocysts matters. They are not deployed randomly, but in patterns that maximize efficiency. Gentle drift ensures that tentacles sweep broad volumes of water without tangling. The jellyfish's body pulses rhythmically, keeping its filaments spread in curtains that increase the chance of contact. Small fish swimming between mangrove roots often do not see the transparent lines until they brush them. At that moment, thousands of capsules fire in unison, creating a micro-harpoon barrage. The venom acts not only as a toxin, but as a shockwave of paralysis, disabling prey within moments. A fish's gills falter, fins stiffen, and it can no longer swim. The jellyfish reels in the filament slowly, contracting muscles within the tentacle, drawing its catch toward the bell. The venom itself is a biochemical masterpiece. It targets sodium channels in nerves and muscles, halting the signals that drive contraction. In humans, this can result in extreme pain, cardiac arrest, or respiratory failure within minutes. The lethality of box jellyfish stings has made them infamous along tropical coasts of Australia and Southeast Asia, where warnings are posted on beaches during stinger season. Yet to the jellyfish, venom is not cruelty, but efficiency. In the dense ecosystems of mangroves, hesitation means losing prey to competitors. By delivering rapid immobilization, box jellies secure food before others can intervene. Survival strategies ripple outward from this weaponry. Their near-invisible bodies reduce encounters with predators, while their venom discourages any that might dare. Sea turtles, among the few creatures capable of eating them without harm, glide through unaffected, their thick skin resistant to stings. For most other animals, the jellyfish remains untouchable. This combination of invisibility and invincibility allows them to dominate shallow lagoons and estuaries, feeding on small fish and zooplankton with little interference. First aid for their stings reveals much about the physics of nematocysts. The capsules fire by osmotic loading, sensitive to chemical and mechanical cues. Vinegar, an acid, can deactivate unfired stingers, preventing additional discharge. Fresh water, on the other hand, creates osmotic imbalance, causing remaining capsules to explode and worsen envenomation. Rubbing or scraping tentacles releases more venom. Effective treatment lies not in extraction, but in halting the physics of discharge. The lesson is counterintuitive. In the aftermath of one of the ocean's fastest strikes, survival depends on slowing the reaction. Ecologically, box jellies occupy a strange niche. They are both hunters and drifters, balancing active steering with passive flow. They rise into shallows at night, when fish move toward mangroves to feed, then retreat during the day to avoid light-driven plankton shifts. Their presence shapes the behavior of prey, which learn to avoid certain shadow lines or alter migration patterns seasonally. They influence plankton distribution by consuming small crustaceans, and in turn their pulses provide nutrients when their fragile bodies are consumed by bacteria after death. They are not apex predators, but keystones in miniature food webs that ripple across coastal ecosystems. From a human perspective, box jellies are paradoxical. They are delicate. Bells collapse at the slightest touch, tentacles tear with ease, yet they wield one of the most powerful venoms on Earth. They are mindless drifters in appearance, yet possess lens-bearing eyes that track contrast edges like rudimentary navigators. They are barely visible, yet command fear that shapes human use of tropical seas, forcing closures of beaches and changes in fishing practices. Their power is not proportional to their size. It lies in the system: transparent bell, visual guidance, invisible nets, and micro-harpoons firing faster than nerves can react. To witness one hunting is to see danger hidden in beauty. The clear bell pulses softly, glowing faintly in dawn light. Tentacles trail like fine silk, invisible until backlit by sun. A school of anchovies darts nearby, and one strays into the curtain. The reaction is silent, instantaneous. The fish stiffens mid-swim, its body locked in paralysis. Slowly, inexorably, the filament retracts, drawing the prize toward the drifting bell. No chase, no spectacle, just the quiet dominance of physics and chemistry combined. The lesson of the box jellyfish is that in the ocean, power is not always visible. Teeth and muscle may dominate one arena, but in the mangrove shallows, transparency and toxins rule. The fish that brushed too close to a shadow line did not fall to speed or strength, but to a system of micro-weapons that fire in nanoseconds. Chemistry rides on delivery physics, The venom matters, but it is the firing system that wins the moment. The reef after dusk is a place transformed. By day, bright schools of fish dominate the scene, parading through columns of light. But as darkness descends, a quieter, busier workforce emerges. From crevices, under coral shelves and across sand plains, armies of crabs scuttle into the open. Their claws click faintly against rock, their bodies silhouetted against the pale shimmer of moonlight filtering through the surface. Some dart quickly, dragging fragments of food to safety. Others parade boldly across the reef, armored and confident, pincers ready for work or theft. They are scavengers, cleaners, engineers, and opportunists, the small but indispensable hands that keep the reef functioning. The most immediate contribution of crabs to reef life is their role in the detritus economy. Carcasses that might otherwise linger, fouling the water, are quickly dismantled by crabs. A fish that succumbs to predation or disease rarely remains intact for more than minutes. Crabs swarm it, slicing with claws, pulling apart flesh and carrying fragments back into holes. Coral mucus, shed by polyps as protective coating, is eagerly consumed, preventing its accumulation and recycling nutrients into the system. This process accelerates nutrient turnover, ensuring that organic matter is broken down and made available for microbial communities, algae, and filter-feeding organisms. In essence, crabs speed the reef's metabolism, preventing stagnation and fueling productivity. Without them, energy would pool and rot rather than cycle. Yet scavenging is only one facet of their ecological role. Crabs are also masters of economy in miniature, nowhere more evident than in the curious behavior of hermit crabs and their shell markets. Unlike their armored cousins, hermits rely on borrowed protection, occupying abandoned gastropod shells. This dependence has produced one of the reef's strangest rituals, vacancy chains. When a desirable empty shell appears, hermits gather in numbers, inspecting it carefully. They tap on the shell with claws, rapping, to gauge its resonance and internal space. The smell of the previous inhabitant adds chemical cues, offering information about condition and suitability. If the shell is too large, smaller crabs may line up in order of size, waiting until the largest moves into the new home and leaves behind its old one. In this way, a single shell can trigger a cascade of moves, redistributing protection across an entire group. It is behavioral economics written in claws and carapaces, a marketplace where supply and demand determine survival. Not all crab activity is cooperative. Thievery is common, and opportunism defines much of their behavior. A reef crab cleaning a carcass may find itself shoved aside by a larger competitor. Hermit crabs may fight for shells, grappling with each other until one is forced to yield. In tide pools, crabs will steal scraps from each other's claws, or raid the feeding grounds of snails, worms, and even sea urchins. This constant competition does not destabilize the ecosystem, instead it drives efficiency. In a habitat where resources are limited and quickly consumed, only those that adapt, negotiate, or fight endure. Beyond scavenging and markets, crabs shape the reef physically. Burrowing species such as ghost crabs and fiddlers aerate sediments, oxygenating layers that would otherwise suffocate under compaction. These burrows provide shelter not only for the builders, but also for smaller organisms that use abandoned tunnels. Sediment turnover stimulates microbial activity, accelerates nutrient cycling, and helps maintain healthy seagrass beds adjacent to reefs. In this way, crabs serve as engineers of the seabed, reshaping the very fabric of their environment. Other crabs defend the reef's living architecture more directly. Coral gull crabs, small and inconspicuous, live embedded within coral colonies. In return for food and shelter, they defend their host from crown-of-thorns starfish, pinching at spines and distracting the predator long enough for polyps to retract. Trapezid crabs, similarly, inhabit branching corals and drive away starfish or other intruders. These alliances mirror the mutualisms of clownfish and anemones, but with claws instead of fins. By defending coral hosts, crabs indirectly preserve habitat for countless other reef inhabitants. Their actions, though small, ripple across ecosystems, reinforcing the resilience of coral structures against one of their most dangerous enemies. Crabs also display astonishing diversity of form and specialization. Some are camouflaged masters, like decorator crabs that attach algae, sponges, and even stinging anemones to their shells, turning themselves into walking fortresses. Others are flamboyant, like fiddler crabs waving oversized claws in mating displays that double as territory warnings. The range of strategies reflects millions of years of adaptation, each design answering the same fundamental questions: how to eat, how to avoid being eaten, and how to reproduce. Their success is evident in their ubiquity. Crabs occupy every niche from mangroves to deep-sea vents, from open beaches to the interiors of sponges. Human fascination with crabs has long been tied to their dual roles as food and metaphor. They are prized in fisheries across the world, yet their behaviors, scuttling sideways, fighting for shells, waving claws, have inspired stories, symbols, and superstitions. On reefs, however, their role is less about symbolism and more about survival. They are the recyclers that clear waste, the thieves that keep competition sharp, the engineers that aerate sediments, and the guardians that protect corals. Remove them, and the reef's intricate balance begins to falter. To witness their impact, one need only observe the reef after nightfall. A parrotfish carcass lies beneath a coral ledge, left behind by a shark's quick strike. Within minutes, crabs swarm it, stripping flesh, reducing it to bone before dawn. Nearby, a hermit crab investigates a new shell, soon joined by others until a miniature trade erupts, each crab measuring, negotiating, and exchanging. In the sandflat, a ghost crab reshapes its burrow, grains falling in cascades as oxygen flows deeper into the substrate. And hidden in the coral, a gall crab braces against an encroaching starfish, its claws snapping against spines as polyps shrink from danger. Each scene reveals not grandeur but necessity, the small acts that sustain the reef's cycles. There is humor in their industry too. Crabs, with their sideways gaits and perpetual scuttling, seem almost comical. Yet beneath the appearance lies a profound truth. Ecosystems depend as much on the small, tireless recyclers as on the great predators. Sharks may define the drama of the reef, but crabs keep it from collapsing under its own weight of waste and competition. They are the unsung custodians, shaping who survives, who shelters, and who thrives on the block. In the end, crabs embody the reef's paradox. They are both cleaners and thieves, protectors and opportunists, engineers and scavengers. They remind us that survival is not a matter of purity, but of adaptability, of filling whatever roles the ecosystem demands. In their claws, a carcass becomes nutrients, a shell becomes currency, sand becomes oxygen, and coral becomes defended. They are, in every sense, the reef's indispensable workforce, recyclers, thieves, and engineers all at once.